I'm sorry. What do we start? 10:04? Okay, welcome. Good morning and welcome to our Accelerator Discovery Distinguished Forum series. Today I'm very happy to, we're very happy to have Roberto Manduchi from UCSantaCruz. Roberto is Professor of Computer Engineering at UCSC. He's an expert in computer vision and he's going to talk about computer vision today. He has a PhD in electrical engineering from the University of Padua in Italy. He's from Italy. And he used to work, before going to Santa Cruz, he used to work at JPL and Apple. This was in 2001, before 2001. He's in the, he's invited, sitting member of the study section on neuroscience vision and low vision at NIH, and is consultant of Aquify, am I saying it correctly? Aquify, and on the scientific board of IRA Incorporated. He has been awarded many prizes. I'm just mentioning one in 2013. He got the Helmholtz Test of Time Award from the International Conference on Computer Vision together with Carlo Tomasi. So today he's going to talk about designing assistive technology. Thank you for being here.
Thank you very much. Little correction, I have not been awarded many prizes.
Yeah.
The prize that I got awarded.
You're too.
But I wanted to mention that. Okay, so thank you very much, Simone, for inviting me. Here it's a pleasure. Of course, we are almost neighbors, so it's very nice for me to cross the hill and come here and see beautiful hills. Did you guys know that when they were deciding the location for UCSantaCruz, I think that Alma there was a candidate. And then I think they asked the students and they said, we want to serve, so they the campus in Santa Cruz. But of course, it's great to be here. And another correction, I'm not going to really talk much about computer vision. I will mention some. But what I'm talking about today is assistive technology for people with vision impairment. And like the title hints, it's going to be a little bit of a personal experience and the path that I'm through. I'm going to tell you something about the few success and the many problems that I had in this path towards trying to build something that can be usable to somebody. Okay, so let's see if the system works. So, because this is personal, let me tell you a little bit where I come from. Besides coming from Italy, and that was said already. Before joining Santa Cruz in 2001, I used to work at a jet propulsion laboratory, which is a great place to be, and enjoy it very much. And these were the types of projects that I worked on. These are a little bit old. Every time I show these, I feel older because technology progresses. And but these were projects related to autonomous navigation, and these were before the DARPA Grand Challenge. For those of you who heard about that, I think that was in 2004 maybe. So these are three types of autonomous vehicles. You probably can tell from the color of these vehicles who was putting the money for this. And what is a common characteristic here, what we were working on, the fact that there were a lot of sensors, all sorts of sensors. We had cameras, stereo cameras, infrared cameras, laser rangefinders, ultrasound, all sorts of things. And these sensors are important, of course, for vehicles to understand where they are, to avoid obstacles. Nowadays, of course, you have the Google car, which still relies on a lot of sensors and a lot of prior knowledge. So when I moved to Santa Cruz, I had a little bit more freedom about the project that I could choose. And I thought, okay, this is great. We learned a lot from these sensors and from this technology. Can we export this knowledge to something that can have some more direct social relevance? And I've always been sensitive to the issues of disability. So we thought, hey, we're teaching cars how to see. Why can't we help a person who cannot see, maybe making use of some of the sensors? This was the general concept. And so I stepped into this field that takes the technical name of assistive technology. It's not a term used very much. If Word will mark the word assistive as non-existing. So maybe it's good if I explain it with the words of a person who used to be a program director at NIH. Assistive technology are services that provide equipment or systems, standardized or individualized, whose aim is to improve or maintain the functional capabilities of individuals with disabilities. And the key word is functional capability. Unlike rehabilitation engineering, we are not trying to fix the impairment. Okay? If I'm designing retinal prosthetics, I'm trying to help you see again. And that's a fantastic worthy goal. That's not what I do. Assistive technology accepts the fact that you have lost some physical or mental functionality and helps you get by with that. Helps you live activity of daily living through support from technology. That's what it does. And that's what we are working on. That's a little bit of a smaller goal if you want to then this grand goal of building prosthetics that can replace parts of your body, cochlear implants and things like that. Now we just try to help you get by through the day with your physical or mental impairments. Now, the next slide, please take it with a little bit of salt. But this is really very true. So, in entering this field, I enter what I call the vicious loop. And I can tell you many people are with me on this. So the vicious loop starts when a person like me, who's an engineer, has done something, and one morning wakes up and thinks, what about what I just did, this particular algorithm, this particular system, why don't I use it to help the blind? What a fantastic, brilliant idea. And so you start working on that, and you do what people in academia do. You start publishing papers, you try to get grants. Maybe you start even running experiments with human subjects. The press is going to love you. The engineer who does good thing for humanity, you're on the front page of everything. And then at some point, when you really try to have the system being used, you discover that people are not really using it. Some people even criticize you. So, why are you criticizing me? I'm doing something for you, right? And there is frustration or resentment on your end with you, the engineer, saying, why don't they, the people who are supposed to use my fantastic tool, why don't they use it? And on the other end, you see people telling you, okay, here is another one of these guys that comes with a useless gadget. So this is what I call the vicious loop, right? And I can, as Simone mentioned, I sit on a almost permanent committee that reviews proposals for the NIH, and I see tons of situations like this. I know it pretty well because I'm the first person who has been here. So, a person with some sensible researcher at the end of the loop just pulls it quick and goes back to the things that this person knows how to do well. Then a few desperados like me keep circling the loop, trying to see whether there is something that we can learn, and at the end, perhaps being able to really build something that people will actually end up using. And so what I'm going to tell you today is a little bit of the things that I've learned, both in positive and in negative, towards this goal.
There's a quote that goes something like, "The perfect is the enemy of the good." And the idea of it is that if something is not perfect, people will criticize it even though it's good, and that's bad for good. So presumably, whatever you design here is good, but not perfect, so it's criticized.
That would be an optimistic view. Well, I'll show you an example that is more pessimistic, to show one example in which, in fact, even though I thought it was good enough, perhaps even just the problem was wrong. The way I would call it is that we often start with a solution in search of a problem, and that's extremely common. The first thing, of course, the first lesson I learned is that you need to know your customer. I really see these types of applications as a sort of consumer market for a very special community that you need to know well. And if you ever worked in consumer market, and I had some experience by working with small startup companies, it's very difficult to really understand what is the killer app, what is the killer tool that people will need, that will find convenient, that costs the right amount of money, and etc. So let's start a little bit with the customer in this case, who are people with visual impairment. So a little bit of statistics. The first pie here shows you, in the United States, all of the population. In gray, you have people with normal vision. Then in this yellow, where is the laser? Here?
The laser is not working on the big
Okay,
screen.
no problem. Yeah. So the yellow cheddar slice there is people, thank you, with good old times, like that. With significant vision loss. This means people who have some trouble performing something, even wearing glasses. These people can still probably drive a car, etc., but they feel that they have some problem with their vision. The much smaller slice is people who are legally blind. That means in the United States that you have acuity less than 20/200, or that you have tunnel vision less than 20 degrees of field of view in your best corrected eye.
Let me ask you a question about significant vision loss. Let's say someone with glasses is fully correctable, so they don't count as significant vision loss even
No,
though...
if you never have problems, if you don't feel that you have problems, but if you feel that sometimes you can really read a sign, that it would be a person with a problem. Legally blind is quantified. It's more of a problem. Mind you, there are some states in the United States in which you can even drive the car even if you're legally blind. So, it's kind of scary. Don't drive there. These are people, it's very, very tiny. It's like about 250 to 300,000 people in the United States who are declared as blind. You will hardly find, it's not so easy to find a person who is completely blind, who has zero light perception. Most blind people you will deal with have some light perception, but you can't do much with just light perception. It can help you quite a bit in getting some orientation because you know where the window is, right? But there are a lot of things you can't. So it is a very small market, indeed. If you just address, as I have done, people who are blind. And here's a funny thing. As engineers, we like simple things. We like simple models. So we tend to like the blind. This person sees or does not see. And it's not a good approach. In part because, again, there are very few people who are totally blind. And in part because we tend to associate a person who is blind with basically a robot. And now I'm going to control, I'm going to give you all of the sensory input that you need. Without realizing a person who is blind has their way to get around, use other sensory perception, mental model, and etc. So if you really want to help a person who is blind, you really need to understand how this person gets by, how this person is able to move in the house, how this person is able to use a computer, etc. Age distribution, just quickly, 1/3 of people with significant vision loss are about 65. I used to call them senior, but I'm getting older, so I don't like that term anymore. But is this important? In part, this is due to the fact that there are progressive diseases like macular degeneration, diabetic retinopathy, that hits you when you get older. Why is this important? Because if you develop technology, people who are older are less receptive to very new things. You're not going to find a lot of early adopters in this population. Some more statistics. Let me just summarize this one here. Not surprisingly, if you can't see well, it is more difficult to get a good education. Think about learning math, geometry, geography, without seeing things. It is a big issue. If you write a formula, you can translate things in Braille. And there exists a type of Braille, Nemeth Braille, that translates formula in Braille. But think about it. Try to really understand a formula if you write it in LaTeX. Okay, you can write a formula in a linear language like ASCII, but to really get it, you need to see it in 2D. Okay, formulas are 2D things. So the whole thing becomes difficult, not to talk about geometry. And I mentioned Braille, and we tend to have the notion that if you're blind, you know Braille. It's not so true anymore, unfortunately. This is statistics about children of less than 18 years of age, I think, that are legally blind, and only a small portion of these children actually learn Braille. Nowadays, unfortunately, Braille is taught less and less, in part because, of course, you have computers talking to you, so we kind of think that maybe Braille is not needed. A lot of blind people think that that's a real pity, that Braille should be taught. In general, you can't expect that a person who is blind will read Braille, especially if you turn blind when you're older. because learning Braille is not easy, because your sensitivity to your finger is smaller, and if you became blind because you had diabetic retinopathy, diabetes also has microneuropathies, cancer microneuropathy, so you really lose a lot of sensitivity. So these are all things that you need to keep in mind. So one exercise that I think you should do is to try to think, okay, you can see well what it is that you cannot do. And these are some of the things. I put them like a Snellen chart here. In more or less priority order, you cannot drive your car. For people who become, who lose their sight late in life, not being able to drive their car tends to be one of the heaviest things. And that's why we need to emphasize public transportation. You can't read the paper, may trip over an obstacle, may miss a sign far away, may not be able to cross a street safely. I have more to say. But they may not find what they're looking for in the supermarket, may get lost in a new place, might not receive a proper education, as I mentioned, and therefore might not be able to find a good job. You might not recognize friends from a distance, which can be a little bit embarrassing at times. You might lose objects in your home, may have problems over the web, might not know who is in the room. Can everybody read this? Because you may not be able to read these lines. Okay, so some other things that you can't do. And as an engineer who wants to build technology to help a person who can see, probably had to pick and choose here and try to decide what it is that you want to work on. Now, I see Ben Shaw sitting there. And Ben, I hope you don't mind if I very briefly show this slide. I wanted to show one slide with the IBM logo here. So this is the result of an exercise that Ben's group and I have been doing about trying to build persona, trying to educate ourselves and imagining how a person who can see the different types, there's a huge diversity among the people who can see, what it is that you would be able to do, not to do, what we do in your life, and etc. So I don't know if I was allowed to show this, I'm going to switch over, but I wanted to show that.
You were allowed.
Okay, thank you. If I'm not allowed here, with us. And if you like bubble diagrams, this is just another one. We tend to strive for independent living, even though I have to say, in my experience with dealing with people with disabilities, diversity is the keyword. So in most of cases, independent living is what we strive for. I know some people who really don't care about independent living. I know people who were born blind, and they are used to people tending to them, and they're expecting that. And if you try to push them into living more independently, they might not be too happy with that. So we have to appreciate the whole diversity that there is. Anyways, for those who are interested in independent living, the four bubbles here are some of the main things we need to achieve, I think. We need to be able to do in our life that is important. Education, employment, travel, entertaining, socialization. And the color bubbles represent some of the topics in which technology can help towards this goal, which are, and I'll talk about several of these: mobility, wayfinding, computer access, information access. And if you wonder what's the difference between information access and computer access, computers are so special in everybody's life nowadays that they really have a particular type of a special place in our life. So accessing computer versus accessing information all around us, in my mind, is a little.
Can you explain independent living? Does that mean you don't need some other person's help? Maybe a dog's helping another person's help?
For example, I was speaking with a person who is used to always go to work with being driven by one of those paratransit systems, rather than taking the bus. This person could have taken the bus. He didn't want to. He wanted somebody to come pick them up and walk with them. Whereas other people whom I know really don't want to go on paratransit. They really want to push themselves and try to do that by independently. So it's a little bit of an attitude that some people have towards. Let me make another example, not related to blindness. I teach a class on disabilities, a large class at UCSantaCruz. And I see disability as a kind of an holistic thing. I had a guest person who is a neurorehabilitation expert. She's fantastic. She deals with persons with spinal cord injury, stroke, traumatic brain injury, and the like. And she was visiting some remote village in Nepal, trying to suggest these people to start using motor wheelchairs. Motor wheelchairs will give you independence if you're quadriplegic. And the people there looked at her and said, look, if somebody here is paralyzed, the whole village comes to help. The concept this person will move around by themselves is something that in our society doesn't make sense. We really, part of the society is everybody will come and help. So this concept of independence that, especially of course in Western country, we value highly, might not be as important in other societies. That's what I meant. Okay, so let me start with some success stories, not from my lab. These are things that work. Technology that does help people who are blind. Screen readers, in my opinion, is number one. These are the first ones, by the way, were developed at IBM by Chieko Sakawa's group in Tokyo. Some of the best and the first readers. These are systems that read the screen to you and allow you to actually interact with the computer to navigate the web. They are not perfect because web pages are complex, but if you think about the difference in quality of life between not being able to read a paper, access information except from the radio and the TV, and being able to interact with the computer, it's a tremendous change. Screen magnifiers are used by people who have low vision. Braille interfaces are very handy for those who can read Braille. They're a little bit expensive, but a lot of people use them. And larger and telescope, again, to read a paper, or this is a system developed at Arizona State that has a camera here that zooms in onto the blackboard where the teacher is writing something. This allows students with low vision to follow a class. Accessible GPS, we use GPS a lot, I'll have more to say about that, as well as optical character recognition, and other tools like Mind Reader, and even object recognition and crowdsourcing. So these are some of the success stories that I wanted to do.
How does your Braille thing work? I mean, it's an interface to a computer? And
This interface to a computer,
Braille?
it creates one line of text, and you fill it with your fingers. When you're done, you press and you get to the next line. So again, this is very handy in social situations where you don't want the computer to really read aloud in front of other people and you don't want to carry a headphone. And for people who are proficient, they love it. Extremely expensive, unfortunately, because this is a mechanical system. A little thing like that is probably $1,500, and it's just one line of refreshable Braille. People are working on big matrices, and they cost a fortune right now. So this is a place where, you know, I'm expecting a big breakthrough in technology, building a big refreshable matrix in Braille that is affordable. So let me start telling you a little bit the things that we've been working on. Let's start with mobility. These terms, mobility and orientation, are technical terms used by orientation and mobility instructors who are professionals, help people who are blind to learn to get around. Mobility, this definition by my friend Richard Long in Michigan, moving safely, gracefully, and comfortably through the environment. It depends on large part on perceiving the properties of the immediate surroundings. So moving safely, gracefully, and comfortably. If you are familiar with robotics, I would say that the equivalent of mobility is obstacle detection, whereas orientation is what in robotics is called path planning. So mobility means being able to walk without bumping into obstacles and trying to walk in a straight line. So the first thing we need to see, okay, how do people who are blind walk? Those who walk independently. Some blind people simply never walk independently. 10% of people become blind, they never leave the house by themselves. Those who do, well, they use the cane, right? Or a dog. White cane is used by about a half of blind people in the United States. Dogs have much fewer users, which is always surprising to me. Also because I know a lot of blind people who have dogs and love to walk with dogs. If you ever see a blind person with a dog, they likely walk faster than you do. Dogs tend to walk fast and straight, and they feel secure with the dog. They know they're not going to bump into obstacles. All right, so, but you know, there are disadvantages all of these. They are really low tech. So how about some more high tech? Has somebody thought about that? Sure. A lot of tools have been proposed. Very few people, if any, ever use them. And undeterred by this information, I thought, why? We are so good at building sensors for 3D sensor and sort of things for vehicle. Why don't we start by building a tool that helps me with mobility? Let me explain very briefly what this tool does. So this was back in 2004 or so. So right now we have range cameras, like Kinect, Kinect 2, or sort of things. In those times, range imaging was a little bit more in infancy. In fact, this system is not a range imaging system. It's a very simple system. That ideally would have the size of a flashlight, even though another implementation at the size of a hammer or a meat tenderizer if you wanted. Good to hit somebody in the head. But those are built with a laser pointer and a camera in what is called an active triangulation setup. Something very simple that by triangulation allows you to precisely measure the the distance of a surface that is illuminated by your laser pointer. Now, okay, unmeasured distances, big deal. Could be useful up to some extent. But what we did was something more. We kind of study the dynamic use of this system. If you look at this picture here, my students then built that. You see it, a line of light. The system really was a laser pointer. So this was a picture taken with longer exposure time, as then was pivoting the system up and down like that. And why would I do that? Well, because if you can measure constantly, real time, the distance to surfaces as you are moving this thing up. Look what happens if you're in front of a step. So imagine that this is a person, this is my tool, and I'm pivoting it like that in front of a step. Steps are very important. If you walk, you don't want to trip on the step. Well, if you measure the range throughout your pivoting it up, this is the range measurement you will have. You will notice a discontinuity here. This is the discontinuity that you have once the laser pointer hits the vertical base. So as you move the thing up and down, and you track also the inclination of this through an accelerometer, and you track the range that you have with your Kalman filter, whatever you want, you will be able to detect discontinuities. You'll be able to tell that at some point there was a step or a step down in front of you.
Does it say to you a number? What does it do?
The system would simply beep, and it will also give you a sound about the distance. Okay, so we spent a ton of time on the user interface on that. In part because we realized something. Okay, this system, we're trying to sell it to people, and the idea, look, this is great. It was funded by the National Science Foundation. This allows you to detect steps much further away than a cane can do, maybe 3-4 meters. And when we were going around to people, blind people, they would tell us, how exactly would I use it? Why would I use it? Well, should I use it instead of a cane? Not together with a cane, but I only have 2 hands. What if I have a coffee cup in the other hand? So we didn't realize that the very low tech, like a cane, can do fantastic things. In fact, a cane can work as a bumper. It can work as a probe to fill the size of an opening. It can help detecting landmarks, but especially line of direction. People use cane to walk parallel to a wall by hitting the wall with a cane so they know the distance to the wall. It can detect drop-offs. It can be used as a measurement tool. But especially, a cane is cheap. It only costs $20. It never runs out of power, unlike a computer. It's light, durable, and foldable, and I like this one here. It always works. Will my computer vision algorithm always work? Not too sure. Identifies a blind traveler and a put driver's light. So this was a big lesson for me. Beating the cane is not something you want to try to do. Will you really feel so confident that your system works so perfectly as to tell a blind person, throw away your cane, just use mine? Absolutely not. And then you run into some issues of convenience. Sure, I can see further away. How important is that? And to do so, I need to have something that I carry in my hand. I need to learn something to use. I need to change batteries every day. All these convenience, cost, size sort of things are very important considerations that made me understand that nobody would ever use a tool like the one that I built. So please don't tell the NSF to pay for this. But this was a great lesson for me. And after that, I realized, okay, next time, first let's get to know more blind people. I became friends with a lot of blind people. I'm kind of known in the local community. These people are very patient with me. And also let's try to find good problems, which is honestly probably the most difficult part of my job right now, is to understand what are problems that I should attack versus those that I should not. And way too often, I'm driven by the fact that I can do something, therefore I will do it. We shouldn't do things just because we can do them. The other big problem, of course, is what I call the academic drift. we start doing something and then we go off the tangent because we can start publishing papers and we find some nice little theoretical problem that we can solve, and that distracts us from addressing the real problem. Oh, by the way, these are tons of things that a dog guy can do, not even compare. Is obstacle detection something they should not care about at all in terms of technology? Maybe not. There has been, for example, an orientation mobility person at the Veteran Center in Palo Alto who told me, look, if you could build this little system that is very small, you attach it on your jacket lapel, and it just does one thing. It tells you when you're about to hit your head against an aerial obstacle. That could be very useful. So the first thing we did this time, we started with the right step. Is it a problem? Is that really a problem? Do people who are blind hit their head against an open cupboard door? We ran a survey with about 300 people who are blind visually and legally blind. We found out that 13% of these people reported a head level collision at least once a month. So there are a substantial number of people who do happen to hit their head. Is it very serious? Sometimes people have to have surgery, sometimes will just hit their head, but it certainly is upsetting, okay? If you ever try to walk blindfolded, you're scared. That's the feeling to describe that. You don't know what can happen to you, and you're really afraid to hit your head against something. So we did start with a student to design a system that was based on ultrasound bilateration. I'm not going to spend much time on that. These are the specifications of the system that would have to have a certain field of view, horizontal or vertical, enough to make sure that it warns you in time before you hit your head. We cannot drop it, in part because my student found a good job in a startup. That's always a problem to keep good students in a booming economy. In part because I am not convinced. I'm not convinced that people would actually use it, because if you hit your head once in a while, are you really going to bring every single day a tool that will have false alarms? Sometimes it will stop when there was nothing. You'll have to change the buttons. You have to remember to put it on every day. People are not going to do it. If you walk in an area that you're not familiar with, perhaps you're going to keep your hand like that. One instructor recommend sometimes to wear hats with a large brim so that the brim hits the obstacle before you. So this is probably also a false lead. Let me talk about then some other types of problems we worked on. The general concept of wayfinding, which is very interesting, also I think an intellectual point of view. So wayfinding, again, as definition, by Richard Long, is the process of navigating through the environment and traveling to places by relatively direct path. As I said, path planning. Is that important? Well, I like the words of Alt Eicher. This guy is the guy who, one of the first guys who designed wayfinding signs that you see at the airport. He actually designed, it was kind of groundbreaking at the time. In 1972 in the Munich Olympics, he started putting these ideograms of representing activities, sport activities, and etc. He also designed the logo of Lufthansa. Less important. So finding the way is not a gift or an innate ability, it's a precondition for life itself, knowing where I am. My location is the precondition for knowing where I have to go, wherever it might be. And if I need to go places, I need to know where I am and how to get there. So, and I also, I had to show this one here. I was in Japan last year for a couple of weeks for a sabbatical, actually visiting the IBM lab, and I happened to visit the Kiyomizu temple in Kyoto. It's a fantastic temple. At some point, I noticed a little square with a love stone. There are two stones separated by something like 10 meters, and here is the sign that says, the stone is called love fortune telling stone. If you walk safely from this stone to the other with your eyes closed, for once your wish will be granted soon. If you can't, it will be long before your love is realized. And it is said that taking advice requires you to have someone who will help you achieve your love. This is a little bit of a strange English, but basically the concept is you need to start from a stone, close your eyes, and try to walk straight to the other stone. Let's see if you can reach it. If you touch it, then your love life is going to be successful. It's a real wayfinding scenario, right? By the way, if you are blind, walking in a straight line is extremely difficult. There are tons of experiments that show that without sight, the reference, you will almost certainly start veering away. The other thing that is interesting is that you can have some help. In fact, there were a lot of kids there playing with this. It was a lot of fun to see them. So somebody would start like this young person here with their eyes closed, and their friends would tell you left, right, left, right. And if through the help of your friend you will reach the stone, this friend has a responsibility in your love relationship. I don't know exactly. So there is, you know, they thought about this probably, I don't know, 100 years ago, and they also thought about the concept that yes, assistive technology, assistive something can be used. Anyway, so the first thing I think that we should think about is how people who can see find their way. Well, I would say there are three main parts here. One is prior information, a map. Okay, we often consult maps to go to places, or we hear verbal direction. The office is 2 doors down and then make a right. Once we are in the place, indoor or outdoors, where we are trying to find a way, path integration is the functionality by which we continuously update in our mind our own position. So here it says continuous update of egocentric coordinates of starting location. But in truth, we are forming an allocentric representation of the environment where we are. Think of a bird eye view. So some of us are able to do that. Some, like me, are totally not able to do that. But if you can do this, it means that as you walk somewhere, somehow in your brain, you are remembering to turn left and right, and you have an organic completion of a cognitive map. Some of us can tell from here where the exit door of the building is. I don't even try. Some of us always know where north is. Some of us know once they go somewhere how to go back. If you can do that, usually it's because you formed a cognitive map in your mind. And to do that, you have to remember that you turn right and left. You have to pay attention to these things. So this is called path integration, which is the equivalent, if you want, to dead reckoning navigation in robotics or in aerospace engineering. The other possibility is piloting. Piloting means referring to the landmarks that are visible, that are sense, that you can access with your sense. So seeing a sign, seeing that there is a corridor there, so you need to take the corridor, noticing landmarks and the like. So piloting is more of an egocentric type of representation. Here I am, I see something there, I go there. I don't need to integrate this into a global view of what is out there. How do people who can't see find their way? Really in kind of similar ways. Some prior information. Maps, if you use a map, they need to be tactile. Unfortunately, tactile maps are not used very much. I think tactile maps are great. They are not very convenient because they are made in paper. They are difficult. I have a little bit more to say about that. Verbal direction, absolutely. And there are all studies about how blind people communicate direction to places differently than sighted people.
So how does a tactile map work? What is it?
So a tactile map is a typical one is made with paper. I have an embosser in my laboratory, so emboss a piece of paper with lines, raised areas, different textures. So you have a more or less of a binary representation of a map. The problem being that there are two problems. One is that your tactile resolution is low. Okay, so the dots need to be 0.5 millimeter wide. So you can't really put a lot of information in it. And that's why, in my opinion, and there's something that I plan to work in the future, you have to think about non-metric mappings. You have to think about maps that maintain the topological information of what you want to show, but not necessarily metric information. If I have a large empty space, there's no point in using all your map for that. If you look at maps of public transportation, for example, very often they're non-metric. They're topological but non-metric. There's no point in taking a whole space for a long stretch. So I think that tactile maps should be used in this way. The other problem with tactile maps is that you don't have a whole view of the map. With sight, you see the whole thing at once. You notice spatial relationships immediately. If you explore a map with your finger, you have to build the spatial relationships. It's like looking at a picture through a pinhole that you move around. Much more difficult to build the whole concept and the spatial relationships. So path integration, I think that if you're blind, you need to learn some type of path integration, but I know blind people who simply don't. They get lost immediately. Some blind people learn very carefully to count their steps, to count their turns. and they know exactly how many steps they will go before they turn right and then left to go to the office. Piloting, which is sensing, sure, as a blind person you also sense, but of course you can't see things. You could read Braille sign. If you can't read Braille, you may notice some landmarks that are mostly acoustic or tactile. Now here is the main thing. Except for acoustic landmarks that are not too common. But here I could hear, for example, the coffee machine going, so I may figure out that maybe it's not a coffee machine. But in general, the perceptual sphere of a blind person is limited to one arm's length. What psychophysicists call the distal stimuli basically don't exist with blind people. As a sighted person, I can see things 20 meters away, and I can get my orientation. As a blind person, this is my world. I can get lost in anywhere. I had blind participants in my studies getting lost in the bathroom and not being able to come out of the bathroom because they were not able to find the door. So there is something we need to really realize how limited the perceptual sphere of a blind person is. So, and one of the main solutions of wayfindings, I think, is probably GPS in general. And many people think that through GPS we solve kind of the problem. It's not the problem. It's not true. In part because the GPS only works outdoors, but also because of the resolution, which is limited up to 10 meters. And here is again, this is connected to what I just said about the perceptual sphere. Look, I took a picture of my building here, but just a little bit over 10 meters away. So that's what the resolution of GPS that we use. GPS would have taken me to the building. Okay, here I am. Now find the door. As a blind person, you probably spend easily 20 minutes walking around until you find this door and bumping into things here and there.
How do you find it?
You would use your cane to move around, and you would probably try to see if there is anybody can help. If not, you will start doing what is called a perimeter search. You're taught that in orientation mobility. Usually you're taught to do that in an indoor space. So if a blind employee came here, probably an orientation mobility person will start walking around this blind person around the perimeter of this room. Why the perimeter? Because you don't want to be in an open space as a blind person. In an open space, you're completely lost. So if you sit here in the middle of this room, you're totally lost. You don't know where to go. If you are next to the surface, you can follow the surface, you can feel the landmarks, start remembering landmarks and things like that. In this situation, if I hadn't been here before, not sure, you would go and bump into things, and it would be extremely difficult to find it. So this, I call it the last meter. It's really difficult. So there is something that we need to absolutely keep in mind when designing wayfinding system. Now, infrastructure can help a lot. And there is infrastructure that support wayfinding. Simple thing is this tactile paving tiles that probably I've noticed in several cities. Now, you don't see these very long tiles very often. I see them in Japan a lot, even though I hardly will see a blind person around. Accessible pedestrian signals, these are the little beepers that you notice in some traffic intersections, and they help you both understanding when is your time to cross, but also they give you an indication of the direction of the landmark at the other end of the crosswalk. Then there have been technology that dated from the 70s that worked really well, but I think it's dead. It's called Talking Sign by the Smith Catherwell Eye Research Institute. It's a technology that uses infrared beacons of multi-rated light. As a blind person, you will hold a receiver in your hand, and if you point it in the right direction and you are within 10 meters or so from this beacon, the system will demodulate the light and talk to you, basically. So this is really old analog technology with a lot of potential. Why am I saying is that? Because it costs a lot of money to replace that. That's the problem with infrastructure. Somebody has to pay for that. And how can you get people to pay for that? Basically, the only way is to make it into regulation, to make it as mandatory by the American with Disability Act. The fact that every room here has a Braille sign and maybe relief letters is because the ADA mandates that. So there's a lot of politics that goes in here. For example, this company here has been lobbying quite a lot to try to have their system be mandated, but they have not been successful, which means that companies are not going to pay for that. It costs too much money to support it. Other proposed systems are RFIDs embedded in for example, here in the soil, under the floor, with an RFID reader on your cane. This is a more recent one. It uses low-power Bluetooth iBeacons. Maybe some of you are familiar with those. Apple has been pushing quite a bit this iBeacons technology. In SFO, in Terminal 2, there is an installation of about 300 iBeacons. The iBeacons are tiny little things that send Bluetooth signal. They only send their ID, not much more than that. They are battery operated. They can last for 2 years. They're very tiny. You attach them, they're cheap. You put them all around, then you train a system to convert information from which IDs I'm receiving to more or less where I am, and that gives you a location that you can access through your iPhone, say, within the terminal. I've been testing that recently, and it doesn't work great, but it's kind of good. And again, this requires some infrastructure. It requires willingness of an agency to work on that. Is there a question?
If you could, or we could probably talk about it later, the cons of like the iBeacons, about like some of the things that you've noticed. Because I'm working with them now.
So the cons of iBeacons, I think the iBeacons work well if you're in a smaller space, like in a corridor, and if you have a good density. What happens, I think, in Terminal 2 is that, like any terminal in an airport, you have a huge space. And so I tested quite a bit, and if you're in the middle of a large space, you receive some information with very low power because this is always integrated with inertial information from your phone, okay? So as you move, as you rotate it, you do some sensor fusion. So if you are close to a place with a 2 or 3 iBeacons, the precision was pretty good. Otherwise, it started drifting a little bit. So all in all, I think I would like to run a user study on the terminal. I talked with the company, Indoor.rs, and as soon as I have some time, I would like to try that. See whether the accuracy it gives is good enough to do anything good. This system, though, needs a map. Most of the system here, like this iBeacon thing. You, in fact, need to train to do what is called a word driving so that you kind of understand if I'm sitting in a certain spot and I see, and as you can see, 3 iBeacons, this is my area. What if you don't have a map? That is something that always intrigued me. Google is saying that it's going to map everything, and I can believe it to some extent, but I don't think that every single building has been mapped or will ever always be mapped. So one of the projects that we're working with some little support from C-Trees was a system that helps you do safe backtrack. So imagine this situation. You're blind, you enter a building, you go to the doctor, and the receptionist walks you to the doctor's office through 3 corridors. And then you're done with the doctor, and you leave the doctor's office, and there is nobody there to take you, and you don't want to go and disturb people, and you would like to walk back. You kind of think you remember how to walk back, and then you get lost. Happens all the time. You get lost, and the moment you get lost as a blind person, you're really lost, because you don't have any more references, you don't have any more landmarks. So what we've been playing with and building is a system that does just one thing. It knows nothing about prior information on the map of the place, but it tracks you as you move around. It does the path integration for you, if you will. And then if you need to go back, it helps you go back. The system detects the turns that you took, counts the step between turns, and also looks at signatures from the Wi-Fi access points that are in there. Just to give you an idea, this is, Simone, when is my stop time here? I want to make sure that I don't.
It's in 7 minutes. We allow for some room afterwards.
Very good. So you know what? I can talk about this a little bit. I think I overshot it a little bit later, and I'm going to just mention this and then a couple of things more. So actually, I'm going to skip this one here. Let's just jump into this one. So the problem with indoor navigation system. There's a lot of interest in indoor navigation. Companies like Google Indoors, Navizone Indoors are building systems that work like your GPS for the car. They have a turn-by-turn direction type of thing. And these systems, I think, have a big problem because, again, you need some spatial context to be able to do something with that. You need to have more of a scene knowledge, not just know that you need to turn left, because that won't help you then to find a door. Imagine, for example, a situation in which you need to go to a meeting in a certain meeting room. You're blind, somebody taught you exactly how to go there, or a system helps you to take the elevator to get to this room. And you enter the room, you made it. You're a little bit early because you wanted to be early. And you're lost. What is a room? There's going to be a big table with chairs around. There's going to be several chairs like in this layout. Is there a water fountain? Where is the projection screen? Low-level scene description is necessary to give context to do things. And unfortunately, sighted people don't need it. A turn-by-turn guidance system is perfect for sighted people because then you can access the context. As a blind person, this doesn't work. So this is where I think computer vision has good potential because it can give you some context in there. So these are some examples of system built by a colleague of mine who works on detecting crosswalks to help a person understand where he should cross. These are work for students of mine who use an iPhone to do three-dimensional reconstruction of situations like this. And also we've been working a lot on text spotting, which is the ability of very quickly detecting text in a scene that can be used as a reference. So it can tell you, hey, there is something here to read. Get closer and use OCR to read that. There's also tremendous potential for crowdsourcing. Be My Eyes, for example, is an organization that has been used by a lot of people, about 100,000 times that has been used by blind people to get help. And it's very simple. You can sign up as a volunteer. If so, if a blind person needs you, they go to this app. And this app basically starts FaceTime, Skype for iPhone. And this blind person will get in touch with you, receive a request for help. This blind person can show you what the camera is seeing. Help me out. I need to find this object. What type of medicine is this? What is on my plate? Where is the exit? And as a sighted person, you have this video related to you, and you can send them information. It's been pretty successful. A company, IRA, that I work with is building something similar. They just completed actually an experiment with 57 people, in which, however, blind person would wear Google Glass, they have a camera, and you will have trained agents who would receive. So this is a blind person walking, this is what the agent on their dashboard see, and you would give different types of information, given a lot of ancillary information that you have from the sensor on the phone of this person. So this is very exciting.
And the crowdsourcing, does the person who gives the information get paid by the person?
So in the Be My Eyes, no, it's all volunteers. With IRA, they are thinking about economical models. They want to build a company, so they're trying to see whether it's going to be per fee, monthly fee, or to see whether people are going to pay for that. The company would pay for that for their blind employees. The economical sustainability of these things, or in general of assistive technology, is always questioned, but they're trying. So let me jump very briefly into the issue of cameras, because we have been played with those quite a bit. I just want to highlight a couple of things in the 5 minutes that I have left. Using a camera as a blind person is a problem, because you can't see, that you find that you can't see the screen of your iPhone. Try to take a picture without looking at the screen, and it's difficult to take a good one. It is a chicken and egg problem. Anything, if we take a good picture of something, the system will tell you something good, but if you can't take the picture of exactly what you want, that is difficult. So we have been studying quite a bit how we can assist people use cameras as a blind person, and I have this big bubble thing here. Basically it says, look, it is complex. If you use a camera, there is action. You have to decide where to point it. There is a system itself which has different characteristics of focal length, field of view, computation. With a large field of view, you can see more things. You don't really have to correctly point at something, but then your angular resolution is smaller. You can't see things far away. You need to get closer to those. And interface is the key of everything, because if I can see through the screen, the system needs to talk to me to help me take better pictures. As an example, we studied this to help a person who is blind go to a particular location where there is a visual landmark. We created this landmark just to make a wizard of all sort of technology in which we pretend that, say, this will be a bathroom sign I need to reach, but to make our life easy, we created these color landmarks that are easy to identify with cameras. And we studied how people are able to follow information on the camera that sees the thing from far away to reach it. So I do have one quick movie that I would like to show, just to give you an idea. Oops. I think, oh, right, I need to use this here, right? Try. yes. I haven't learned exactly how to do it. Try again. There we go. So if I
Okay,
control Enter.
let's do control alt.
And then next one. Perfect. Let's see if this works. So you hear a person, thank you very much, who is using the phone to try to find one of these targets. The phone will beep once it starts seeing that. Oh, the audio is not on. Now, we missed quite a bit of that because we didn't hear when the camera was speaking. But what I wanted to point out here is that it's a difficult thing. You have to first search, then you may find something. You need to follow your arm through your proprioceptive capability of doing that. But typically, proprioception is not very good if you don't have good sight. And at some point, you lose the target. Your camera has a limited field of view. You have to research that. So, can you go back to your text? So, there's a lot of activities that go into something that we think should be super easy, right? You just follow the camera. No, there is a search part, there is a guidance part that occurs once the system has something and starts beeping and directs you.
How the camera know what to beep at?
Well, in this case, we designed it to detect a particular landmark. So in the real world, you would remember we studied, for example, text spotting in the wild. So if the system sees a sign and needs to read it, OCR wants good resolution. So you will be guided towards taking a better picture, getting close to this object and take a picture of that. My last example is about reading text and OCR. I think you are familiar with optical character recognition, which works pretty well when you have a good picture of what you're doing. And there are apps that do mobile OCR. Here is a couple of examples. They really work well, but you really have to take a good picture. Some of these accessible apps do what I call an opportunistic discovery. They help you with that. It's very similar to, I don't know if you ever deposited checks with Bank of America or other things, where there's an app on your iPhone where you have to put it over the check and at some point it snap a picture for you. And it also gives you some big indications. My wife always gets mad when she tries to use that because it works really well. These systems try to identify, so what they do, they process images real fast. They're trying to understand when is a good time to take a good snapshot. How? For example, because they see the 4 edges of your document, and they say, okay, all the documents in the picture, or because they do some text spotting, they figure out, oh, there is some text here. Okay, this is time to take a snapshot. But they don't work so well for blind people. Everybody I talked to has been fairly frustrated with the system. So we designed a system that can do some guided OCR. It gives you directions. How does it do it? Well, the idea is very simple. Here is one of our tests, and I'm not going to show the video because we're late, but we ask people, okay, try to move the camera to a point where you can take a good picture and then OCR will read for you. Our system has some guidance that would look at the text, try to figure out whether the whole text in the page is imaged. How does it do it? It looks for text using text spotting algorithms, and it figures if there is enough white margin. If not, it gives direction. Raise, lower, move to the left, move to the right. So this, you can see, is a smarter interface that can help you point the phone, get a better picture. So it's a whole interaction that we have. And what we found out, these experiments take a ton of time. As an engineer, I've never been taught how to run human real experiments. And it's something that I'm learning. It's fascinating. You learn a lot. You have to spend a ton of time. We had, in this case, 9 different participants. We actually designed the protocol experiment. What we learned is that, not surprised, without any sort of assistance, using mobile OCR is almost impossible, very difficult. And having some sort of guidance does make the whole process more efficient than these other more simple opportunistic discovery types of modalities. But the interesting thing is that our system can also be used to train a person to do it better. So we had person try to take a good picture of a document without any assistance from the system. Then, with the system guiding them, then let's try again without a system. The third time around, they were so much better. So the system helped with training, and training is tremendously important, right? Because you can learn a lot of things. You can learn how to take a good picture, get the patient to try multiple times with somebody telling us, okay, this is a good location. The system in this case has the promise to be good for training. I think I went over time, so I wanted to thank my sponsor, which is the National Institute of Health, and also I wanted to mention that if any of you is interested in this type of subject, is interested in collaborating, especially for what concerns intelligent infrastructures that can help blind people, people with disability in general, get do the activity of daily life better, please talk to me. I would love to hear. Okay, thank you very much.
Any question? No more questions?
Yes,
One question.
just one. At the end, you talk more about mobile phones. Is there any particular type of smartphones for blind people? Because as you don't have buttons, you don't even know if you have an alert in there that's blocking your interface. But I think there's not much market for that.
So when the iPhone came out, I immediately thought, okay, this is definitely not accessible. You can't feel the key. Blind people love the iPhone. Most blind people. And in fact, they still use much more iPhones than Android. So it's a surprise to me. And this is due to two reasons. One is that Apple has been really smart. And for the second version, the iPhone, they introduced VoiceOver, which is a screen reader for a Mac, but it works on the iPhone. And if you guys have an iPhone, if you want to spend 5 minutes, go to System Setting, Universal Access, VoiceOver on. It's a little bit frustrating because then you don't know how to go back on anymore. But the great thing is that as you explore the screen with your finger, this reads the icon for you. You can even input text. That takes a long time, but now there is Siri. So, the iPhone is actually more accessible than we may think. It is not perfect by any means, but people are willing to go the extra mile. Why? Because if I use the iPhone, it's exactly the same system that you as a sighted person are using. And I can use Facebook and use email with the same tool that you're using. The level ground is even now. So this psychologically is tremendously important. People love it. So I don't know, I haven't heard of anybody trying to now build. There are in case, there are some type of smartphone, regular phone built for elder people who are not very good at using all these bells and whistles. And you could think maybe they could help also a blind person because they're big keyboard. I don't know any single blind person who can, but they all want to use the iPhone. Thanks.
I have a question. So is there a preference of blind people towards cell phones now, smartphones over computers? So now I'm thinking, for instance, about web pages, right? So mobile web pages are much easier to navigate because they're essentially mostly text.
Okay, good point. I don't think I know the answer to your question. I don't know that navigating a web page in general is difficult for blind person, especially with these super cool web pages we have nowadays. There's a lot of interactive content. So I haven't thought about the fact that the effort of making the web page accessible on a cell phone forces the developer to get rid of a lot of this graphical interface, and whether that makes it easier for a blind person. Honestly, I haven't thought about that. It's a good question. I would ask around.
And there are the ebook readers like Kindle that will textify a whole web page for you, removing all the images or making them just static instead of dynamic.
So the textifying web page is part of the screen reader. So if you have a Mac, VoiceOver will do it for you. It is always difficult to textify web pages. Why? In part because many web pages are image-driven. So if you don't give a description of the image, you don't do anything with the image, and sometimes if you don't see the image, you can't read it too much. In part because of the whole layout of web page is very complex, it's like a table. So there is a lot of studies about how to read web pages, how to make web pages that are accessible, actually. So in that sense, I would say that is not just for the e-readers, that is technology being developed in general for all for computers. The standard is for PCs is something called JAWS, which is made by I don't remember the name of the company, but it does all of this work. And in general, the whole activity of screen reader is a complicated software engineering activity. Because if you, for those of you who understand these things, you need to access what the screen is displaying. How do you access that? Well, now operating systems have what is called an accessibility API that supposedly goes and grabs all of the user interface elements and provides a handle for you to access those. But even so, it is not very easy because the whole interaction, I don't know, if I click on something, something else happens on another window. How am I going to read that thing to you? So all of this interaction makes it difficult to navigate.
I heard a TED talk before about mapping color to sound. The speaker is color branded. He couldn't appreciate the beauty of a colorful world. So he had the idea of mapping those colors to different sound. So when he saw painting a picture, it will directly abstract that picture to a mix of sound.
Okay, so this is interesting. So it enters the whole realm of sensory substitution, where we're basically trying to use other sensors to supply, and all of that I described in a sense is sensory substitution, but I do it at a highly semantic level. That is, I am telling you, I have system talk to me most of the time. It depends on whom you ask how the things work. Okay, people that try to sort of think. They started with Bakirita back in the 70s, who had a system with a camera, we're talking analog things, right? And an array of electrodes on your back, and the system would translate a black and white picture into stimulations of these electrodes on your back. And it showed that people were able to kind of make up some shapes. So it has to do with the plasticity of your brain, in which, you know, there are all these theories about, okay, inside my brain, the visual information is something separate from the tactile information, or is there a common intermediate channel, etc., etc. What I would say is that so far the system have shown that in some particular cases, and you get the typical case study where in a room there is a black obstacle, and you show that people are able to avoid the black obstacle because they have information on the back, on the tongue, on the forehead, because they hear it, like in the colors, etc. Would they work if I take a picture of this room? The picture is so complex. The things that are here are tremendously complex. Can I really make out what is in the picture, make it into usable representation? I honestly doubt that. So I'm a little bit negative on these low-level sensory substitution systems. I'd rather have that picture tell me semantically what is in there. I think it will make more sense. Thanks.
My question is on the commercialization and monetizing. Like, if you, I think there are few researchers, engineers who just really care about like the quality of life, you know, improving one's quality of life. And I personally don't think that assistive technology won't receive the reception that it's supposed to until there's some motivation, right, for a developer or for a group to go after it. So I was wondering, have you seen any models that have worked to commercialize or monetize like assistive tech? Or from your experience, what could, like a possible solution, like a hypothesis? Like,
it's a great question. The sustainability, market sustainability of assistive technology, is a huge issue. Mm-hmm. So there are very few companies that have been able to make money means to survive, right? Because you can't do this. Maybe you can do. Be My Eyes is very successful right now. You always rely on volunteers. The quality of assistance you get is not really clear, but right now it is a good example of something that is somehow self-sustained. Will that last?
Okay.
Beside it, in terms of company, look, there is Freedom Scientific, I can't remember the name, sells some of these screen readers, and that company is making money. It has a monopoly. It really elbows out anybody else who tries to enter the field. I would say it is really tough, in part because there are few people who are blind. So if you address low vision people, there are many more. Some of these are retirees who might have made a lot of money in life and lost their sight later. So there's a company from Israel called Orcam who has now full hardware system with a camera here. It does OCR, there's a beautiful user interface. It is for low vision people, not for blind people. It costs $3,500. It's very expensive. They might have a chance because the market is larger than just for blind people, and again, whether it is professionals. But if you look at blind people, these people don't have money. They live off disability. There are very few. Many of them have other problems. So how do you build a sustainable market? It's complicated. So there are different models, right? One is, well, let's have Windows, Microsoft, in those times when IBM was doing computers, IBM, etc., extend the operating system to have an accessibility layer. The cost is going to be relatively small. It's going to look good for the company. So this model works so and so because it's still, if you have software, you support it. If you don't support it, it doesn't work. So I don't think anybody has a solution. Because I'm collaborating with this IRA company that has agents who can send advice through data relayed from Google Glasses. And this company has been started by people, by a person actually, who is a serial entrepreneur who has lost a part of his sight. So this person knows what he's talking about. I'm really curious to see how they're going to pull it off into a sustainable market. For me, it's going to be a very, very interesting experience. But you really hit the right spot because it is one of the biggest issues.
Thank you. Do we have more questions? No? Let's thank Roberto again.
This is beautiful. This is great. Thank you very much. Very nice. Thank you very much for inviting me. It's been an honor.
So I'd like to join you for lunch. So when,
Yes.
when will you believe?
I'm not. Unfortunately, I can't because I have a committee meeting in 2. And it's the first one of the year and I can't miss. And I'm teaching it 4.
No.
Apologies.
Thank you for coming.
Thank you very much for first day for the whole time.
Sorry. It was my
I
fault.
just had no idea.
Oh, okay, no problem.
I
Well,
read
good
the
for
people.
something.
It's terrible.
He said doing much, but what are you doing today?
So, the boss always tells me.
Oh, okay. What year
It is, right? However, it could be also a damnation because it's
Okay.
a never learned.